Okay, good morning, everyone. How did the homework go? And any questions do you have? Just put them on the chat, so by 9 we can start. Okay. All right. Let me write them down. Give me a sec. So 2.8. B. And worksheet. Okay. Number 3. Okay. All right, so we start. I'll start with the one in the book, which is 2.8, number 3. And I'll draw the picture and then we get started. So remember, what's a subspace? We have to have a the definition in our mind. So I will write it and we refer to it all the time. So the idea is that we have a collection of vectors in R2 or R3 that have a certain property, so special type of vectors. So they form a subspace if this collection have the 0 vector in it, and so H subspace if, so the 3 property that the 0 vector should be one of those vectors that satisfy the property. If X and Y satisfy the property, then their sum should. And if you have any vector that satisfy the property, then if you scale it, this property is also satisfied. So that's the definition we have for a subspace. So now we look at number 2.8 in the book and see what is going on. So number 3, they give us this picture. It's like a strip right there. That's H. So every vector whose tip falls in this region, this is in H. That's what this picture means. And the question is, why this is not a subspace? If it is, justify. If not, why not? So we go through the list of vectors in this subspace. First, 0, it's right there, is in H. So property number 1, I can say check, it's satisfied. Now, property number 2. If I take 2 vectors in the strip, what does it mean, the vector in the strip? It means the tip of the vector is in it. That's really what it means. It means if I take 2 vectors within this region, and then I take their sum, which is a whole new vector, will their sum be in the region as well? So use chat to tell me yes or no, or unmute yourself to justify. I'll give you, you don't need more than 30 seconds. What do you think? So question number 2 is, if X and Y in H, any, is their sum also within it? All right, I really would like answers so we can move on to other problems. Yes or no? What do you think? No, vector addition doesn't work. Agree with him? Absolutely so. And this problem is purely geometric because they don't really have an algebraic description for it. So this is one vector, and this is another one. Within, no, this is really doesn't, sorry. This vector, and because if I take their sum, we're definitely lying here. So my H is not really, this one doesn't work. So I'm going to take that vector, those 2 vectors. This is, we need 1 example to satisfy. This is X and this is Y. If I add those, so I'm going to add them, addition. So that's the addition, which is absolutely falling outside H. So this is my X, this is my Y. I add them, I am totally outside my H. That's not a subspace. That's the end of that. So you don't have to go any further. So once you give me 1 property that fails, it's not a subspace, and you don't have to do anything anymore. So how you show it's not a subspace, you show me that by an example that one of the property failed. Not all of them. If one of them failed, you're done. That's not a subspace. Okay, any other questions about this problem before we go on? All right, so now I go back to my worksheet and I will see what we have. So I have a question 3 on 2.8 and number 2 on the worksheet. So let me pick up our worksheet and look at number 2. Oh, number 2. Okay. All right, so I'll start here. Okay. So this time I'm giving you your subspaces, or I'm giving you those collection algebraically. And let's start. So my first one is, I gave you H is all vector x1, x2, such that, so this is the particular vector I have. When you add their entries, we get 1. So this is my H. And the question is, so for example, if I tell you, give me 1 vector in H, one of them, who can give me 1 vector in H? Every vector, H, or every vector, is that the sum of their component is 1. So
0, 1.
0, 1, 1, 0, that's in H. However, 1, 1 definitely is not in H because the sum of the component is not 1. So now the question, is this a subspace? Quickly.
No.
No. And remember, we have 3 properties. If one fails, we're out. It's not a subspace. Which properties fail?
It doesn't contain the origin.
Right. If I take the 0 vector, the first one, that's 0, 0, 0, not in H, done, H, not a subspace. 1 property failed, we're done. Okay. Now we're going to look at B. I have here, what's going on here? Yeah, thank you. Very good. Nothing worked. 0 is not in it. I am done. I move on. B. H this time is all the vector. x1, x2, such that the first component is larger or equal to the second component. All right, now is this a subspace? Okay, we're gonna start. First property, the zero vector. Is this in H? It means is the first component larger or equal? That is equality here. So 0, check. All right, we have to move on. This doesn't tell me it's a subspace. It just tells me, you know, maybe yes, maybe no. We have to check other property. All right. I don't know. Anybody have any input? Let me check addition. See if it works. All right. So it means I'm going to take two vectors that have the property. The first larger than the second. And I'm going to take y. y1, y2. The first larger than the second. And now I'm going to add them. When I'm adding them, I'm creating a new vector. It's very new. Its component is x1 plus x2. X1 plus y1 and x2 plus y2. All right. Is this in H? Yes or no? Please the chat. It means, do the component of this new vector satisfy the properties that vectors in H have to have?
Yeah.
Because, yes, because what's going on here? X1 is larger than x2. y1 is larger than y2. Because the vectors I'm starting with are something like 3, 2, x1 larger, and the other one like 5, 4. The first component larger. So when I'm adding them, 3 plus 5 will have to be bigger than 2 plus 2. That's 3 plus 4. That's the picture. So here we say that x1 is larger than x2. y1 larger than y2. So x1 plus y1 larger than x2 plus y2. So x plus y in H. So closed under vector addition. Is it a subspace? I still don't know. I still have one property to satisfy. So finally, the last property. X, let's X be in H. And it means the first component is larger than the second. And now I'm going to scale it. I'm going to scale it. When I scale it, I have a whole new vector. The components are different. Will this new vector be in H? It means if C is any scalar, will the first component C of x1 will be necessarily larger than Cx2, granting x1 bigger than x2? Yes, no, justify.
For example, so you had your vector being 2, 1. If you had a scalar of -1, you would have -2, -1, and -2 is not greater than -1.
Absolutely, that's where the problem is coming from. If C is negative, because if x1 bigger than x2, when I multiply, I use red button. When I multiply x1 by x2, this does not necessarily hold when C is negative. So we think it's no. So now when we reach this stage, we realize, you know, this is not going to hold. So you can either just tell me that C has to be, if C is negative, it fails. That's one way you can go. Or you can give me example. So when we hit this stage, we realize something is wrong. Now you give me example. Take C to be -1 and X, we have to be very, very careful. My X have to be in H. It means the first component of X has to be greater than the second. Otherwise, it doesn't work. And now when I compute, so X is in H, definitely. But when I stretch it, minus X, which is -2, -1, not in H. So absolutely not a subspace. Now, if you had paid attention from the beginning that this is going to fail, you don't have to go to do everything else. But if you didn't, fine, you can do all the work, and then you realize you're absolutely having difficulties at the scalar multiplication. H not a subspace. Not a subspace. And graphically or geometrically, how can we visualize this H? I don't know if you guys know. This is the line x1 equal x2. And x1 greater than x2 is going to be this region right there. That's as if you take any point here, the first component is going to be larger than the second component. So it's basically this half plane. That's geometrically what H is, and that's why it's not a subspace. It's close under addition, but it's definitely failing the scalar multiplication. Okay. So I will look at the other tools because this is kind of new way of thinking for us. And again, I will look at number B, E, whatever, C, sorry. Please, as we move on, feel free to ask any question you want. So my H now consists, now I am in R3, but it's the same principle. So x1, x2, x3. So all the vectors that have the property that when I multiply the component, I get a 0. Okay? And the question is the same. But before we answer the question, it's sometimes nice, or it's good for us, for me, for you, for all of us, to think a little bit what type of vectors are in H. So before I even start the problem, just to understand what H is, let us think a little bit about vectors. What are the vectors in H? So who can give me a vector in H? So just to a little bit understand what are we talking about geometrically. Okay, who can give me a vector in H?
0, 1, 1.
0, 1, 1, that's a vector. Okay, anybody else? Anybody else?
The 0 vector?
The 0 vector, absolutely is it in it. We're gonna have to check that again and again. Anything else?
2, 1, 0.
2, 1, 0. Okay, so how can a vector be in H?
One of the components has to be 0.
One has to be 0. If the product is 0, it means one has to be 0. One has to be 0. So, okay, I'll ask you a little bit later geometrically what is H. We should be able to do it. So is H a subspace? So first, the 0 vector. Okay, you guys already told me that it is in H. Okay, now what about addition? If you have two vectors that satisfy this condition, the product of their component is 0, will adding them also have the same property?
No.
Okay, I hear no. I want on the chat your answer. What do you think? No, no, no. And let us see. If you say no, so close under addition. If we say no, what do you have to give me? You have to give me two vectors in H. You add them, you have a whole new one. And this whole new one should not be in H. So everybody is telling me no, absolutely correct. So I want the vectors, which is basically staring at us.
For the vectors, yeah, you can just use 0, 1, 1 and 2, 1, 0.
Exactly, exactly. 2, 1, 0. These are the vectors. So when I add them, so this is in H, this is in A. That's why sometimes it's helpful to see what kind of vector are we looking for, so to really understand them. And then I'm gonna add them, and I'm getting a 2, I'm getting a 2, and I'm getting a 1. Absolutely, it's not in my it's not in my collection because the product of the component is actually not equal to 0.
So it'll only be in the subspace if both the addition property and the multiplication property match?
It's not in the subspace. H will be called a subspace if all three properties hold, all of them. 0 in it, this hold, and this hold, it's a subspace. If one of them fail, One of them, I don't care which one. It's not. It's not a subspace. Did I answer your question?
Yeah, that answers it.
Yeah, okay. So now it doesn't satisfy this property. I'm done. It's not a subspace. I don't have to go any further. I don't. I can stop. If B were satisfied, I'd have to check C. If C is satisfied, fine, it is a subspace. If not, it's not. Now, geometrically, can anybody figure out what H is?
It would be the x1, x2 plane, the x1, x3 plane, the x1, x2, x3 plane.
Right, it will be only the 3 planes, because if this is 0, it means x1 0, x2 0, x3 0. One of them has to be 0. It means either x1 0, it means my vector should be in the x2, x3 plane. x2 0, it means it has to be the x1, x3 plane. x3 0, it has to be in the x1, x2 plane. So these are only the planes x1 0, x2 0, x3 0, and there is nothing, everything in between is not obtained. So it's this plane, and that plane, all 3 together. They do not form a subspace, absolutely not. All right, any question before I look at the last one and then we proceed? Okay, so my last one was, this is just pure algebraic manipulation, just to x1, x2, x3, and they have the following properties. If you take the first component, you add to it twice the second component, and you take away twice the second, minus 3 the first, equal to 0. And is this a subspace? Before I go any further, for those who have 261, and by now I imagine all of you are either headed or you're taking Calculus 3, what is H? I'm going to remove x1, x2, and x3. Suppose I call them x, y, z, because this fits more into your intuition of Calculus 3. So H is all the x, y, z, to think about all the point x, y, z, such that x plus 2y minus 3z equal to 0.
Is it a plane?
It's a plane. H is nothing more than a plane. Which plane? Is the plane x plus 2y minus 3z equal to 0. Means all the points that satisfy this condition. And that is the plane, there is 0 on this plane. Is 0 a point on this plane?
Yeah.
Absolutely, because 0, 0, 0 satisfy this condition. So this is absolutely nothing more than a plane in R3. It's a plane through the origin. So do you expect it to be a subspace? If you just now visualize it geometrically, if you have a plane through the origin, it has to be through the origin. We will prove everything algebraically, but I want your intuition clear. If you have the plane through the origin, just simple old plane, but it's in R3. That's my plane. And it contains 0. So if I take 2 vectors within the plane, 2 vectors, and I add them, remember, that's the origin. Is there any way I can leave the plane geometrically? So if my 2 vectors are on this flat surface, that's what a plane is. When I'm adding them, I have to stay on this flat surface. There is no way I can leave it. So if x and y in H, their sum has to be in H. Also, that's the geometry before I do the algebra. If I take a vector in this plane, in this flat surface, and I take it, I'm always starting from 0, and I stretch it, there is no way I can leave this flat surface because the plane is the whole thing. It's not part of it. Whether I scale it with C positive or I scale it with C negative, it doesn't really matter. We're going to stay within the plane. So the subspace is really a generalization of the idea of a plane and line and R3 that go through the origin. So that's really the geometry. The algebra is a little bit, it's not really hard, it's just algebra. So let us check it algebraically. But the geometry is absolutely crucial because I want you to visualize a subspace. I want you, when I say the word subspace, I want you to see a plane through the origin. If I'm taking subspace of R3, a plane through the origin, a line through the origin, all of R3 because this helps our intuition. All right, this being said, let us make sure algebraically it is a subspace. First 0 is something in it, 0 is in H. There is nothing really into that because 0 plus 2 times 0 minus 3 times 0 is 0. There is nothing into it. And now I'm going to move to the sum. So I'm going to take x to be x1, x2, x3 in H. Sorry, I would rather start a new page now. So I'm going to take the following. So H, all vectors such that the first plus twice the second minus 3 times the third equal to 0. So those are my vectors. All right, so now I'm going to take 2 of them. So I'm going to take the first x1, x2, x3 in H. I'm leaving an empty space because I'm going to say, what does this mean? And I'm going to take y again in H. y2, y3. It means x, the component of x satisfy this condition. The component of y satisfy this condition. So finally, I'm going to add them up and ask myself, will this new created vector, totally new one, I'm creating a new vector, does this new vector satisfy this condition? What does it mean satisfy this condition? It means if I take, that's my question, if I take the first component, I add to it twice the second, and I take from it 3 times the third, will this equal to 0? That's really my question. Is this equal to 0? Granting that we know this. Okay, so how did the algebra? Basically, I'm going to use those 2 conditions to convince myself either way that this one is 0. So my question is this 0 or not 0? If it's 0, I'm fine. If it's not 0, I try to find an example to show that something is not really well. All right, so let's see, this is equal to 1. I'm going to rearrange the terms so that I can use this property here. That's really what I'm going to do. So I'm going to rearrange them. First, I'm going to distribute my 2. So it's really, really algebra at this stage. I distribute it. And then I'm going to start combining because I know that the x's are particular x's, not any x. And I know that my y's have a certain property. And now I am done. This is 0 because x in H. Because my original vector x is not an arbitrary vector. It's a very specific one. Very, very specific one. So my x is, for example, I don't work with example, but this is my x. So my x, for example, I don't know, I want the first component plus the second. So if I put here 1 plus 4, 5, and I'm gonna take this minus 5/3. This is a vector in my subspace. 1 plus 4, 5, minus 3 times, so plus, minus 3 times 5 over 3, that's equal to 0. So very, very specific vectors, not anyone. So finally, I am right here. This is equal to 0. This is equal to 0 because y is in H. It means the whole thing equal to 0. So my new vector is in H. Addition is satisfied. Finally, scalar multiplication. And then we can, so geometrically, we have the intuition. Now, algebraically, we are proving it. So finally, the scalar multiplication. So I'm going to start with a vector. And in H, it means this vector is not anything. It does satisfy this property. It means the component, if I take the first component plus twice the second minus 3 times the third, I'm going to get 0. So this is a very specific vector in R3. Now I scale it. I create a new one with a new component. And the question, will those new components satisfy the condition? All right, so it means I'm going to take the first and I'm going to add to it twice the second, and I'm going to take minus 3 the third. I ask myself, if this is satisfied, will this new one be satisfied? It means, will this new piece equal to 0? So what's the key word? Absolutely what you want me to do. I want one word. One word. Everybody said yes. Everybody factored the C. End of the problem. So this is absolutely a subspace because it does satisfy all the 3 properties of the subspace. Okay, so this is how we algebraically work with those. If I and as I said last time, the subspaces of R3 are going to be basically the 0 vector is a subspace. Line through the origin will be subspaces of R3. Plane through the origin is subspaces of R3. And finally, R3 itself is a subspace of R3. So that's all the subspaces of R3. So it's the idea of generalizing the notion of planes and lines. That's subspaces. Generalizing the ideas of planes and lines. That's really the idea. All right, now before we move on, we're gonna take one subspace which is actually associated to a matrix, which is an important subspace. So I'm going to work with one of them. The book has 2 examples. I work with one, which is I will need later on. So example of a subspace associated to a matrix, the null space. It's a very easy subspace, but important. So what is the null space? Something we've seen before, but we did not call it the null space. So let A be a M by N matrix. The null space of A, denoted by null of A, is the set of all solutions of the homogeneous system AX equal to 0. So the null of A is nothing more than all the x's that solve the system AX equal to 0. So we have a system AX equal to 0, and I'm only focusing on all the solutions, which is something we have seen before. So, but let me, okay, I'll take example. So suppose A is the following matrix. Try to understand what the null means. And I pick this vector, 2, 1, minus 2. Is X in the null? What does it mean? The null is all the vectors such that A times X equal to 0. So there are a lot of vectors in. So if I have a matrix, this matrix 1, 2, 2, minus 3, 4, minus 1, what's the null of this matrix? All the solution, all the vectors that satisfy AX equal to 0. So is X in the null? It's nothing more than I'm asking you, is A times X equal to 0? It means does X satisfy the condition AX equal to 0? So I multiplied A by X, I computed it, I get 0, X in the null. So those questions, just to understand what the null is. So X in the null, it means does it solve the system AX equal to 0? Now example number 2, I gave you another matrix. Sorry, I gave this matrix, and now I'm asking you find a non-zero vector in the null. What am I asking you now? What am I asking you now? Remember, the null is all the x's such that AX equal to 0. So in my particular case, it means I'm going to ask for all x's such that this one equal to 0. Now this x should have how many components? So I'm asking you the x is at a times x equal to 0. It means this one should have 3 components. Means all x's in R3 such that ax equal to 0. So now my question is, find a non-zero vector in the null. It means give me example of a vector such that a times x equal to 0. So basically I'm asking you to solve the system. So I solve the system 1, 2, 3, 4, 5, 3. I go to my echelon form as usual. You're gonna have to do that again. So these are my leading. I solve. I have x3 to be a free variable. I solve for it. I get x to be a certain scalar times 3 minus 1, 3. So there are a lot of vectors in the null. Every scalar multiple of that is in the null. So one non-zero vector, you pick t equal to 1, gives you 3 minus 3, 1. Okay, so what is the null? The null is, again, you have a matrix A. The null are all the solutions, all those such that ax equal to 0. Something we've seen before. We give them a name. All the solutions of the homogeneous system, we give them a name and we call them the null of A, which are the solutions of the homogeneous system. This is an example of a subspace. What does it mean? It means first 0 in the null, and it means that if 2 vectors satisfy ax equal to 0, their sum will satisfy. If you take any vector such that ax equal to 0, scale it, you get another solution of the homogeneous system. So let us verify that, and then I will talk a little bit more about it. So if A is a n by n matrix, then the null of A is a subspace of R to a power. Now I'm hiding the power because it's crucial for us to understand where the power is going to be. So vectors in the null should be in, so if A is m by n and x in the null, look, my question to you is how many components x should have? How many components? Because we have to know where we are. X in the null, it means A times x should be 0. So x, how many components should x has? Put it on the chat, absolutely n component, because this is m by n, this has to be n by 1. So we have to know where my vectors are. So here I said if A is m by n, so my vectors now, the null is a subspace of Rn because vectors in the null are in Rn, and it's very important to know where are your vectors. So let's check very quickly why it is a subspace. First, the 0 vector is in the null. Why? Because A times 0 equals 0. It means the 0 vector satisfies the equation ax equal to 0. Second, if I take 2 vectors in the null, it means if I take 2 solutions for the system ax equal to 0, then I look at x plus y. That's a whole new vector. The question is x plus y also a solution? That's what it means to be closed under vector addition. So if x and y in the null, we have to show that x plus y is also in the null. All right, let's do that. Suppose x in the null. It means x solve the system. A times x equal to 0. Y in the null also. Ay equal to 0. So now if I look at A times x plus y, will I get 0 as well? So if I have 2 solutions of the homogeneous system and I add them, will I have another solution? And let's see. If I take A times x plus y and I use the property of matrix multiplication, we know that we can distribute. So it's ax plus ay. Ax is 0 because I'm starting with a vector x that solves the system. Ay is 0 because I'm starting with a vector y that solves the system. So I have 0 plus 0 equal to 0. It means x plus y is in the null. For you, it means if I give you two vectors that solve the homogeneous system, and homogeneous system is important, equal to 0, their sum is also a new solution to your system. So you already have another solution. And finally, is it closed under scalar multiplication? So suppose I start with a vector in the null. I start with a vector that solves the system, and I scale it. Well, this new vector solves the system as well. All right, I check. Suppose I take A times Cx. Will I get a 0? Again, I use multiplication. The scalar could be moved out. That's linearity, times Ax. But Ax is 0. So that's C times 0 equals 0. And this is 0 equal to 0. So what does this tell you? If you have a vector and you're solving Ax equal to 0, so you have a system that solves, it's a homogeneous system, and you have one solution, then this is telling you if you scale your solution, you get another solution of the homogeneous system. So, and this is what my last question here is about. So what does this tell us? Tell us that if X and Y are in the null, that is, if X and Y are solution of the homogeneous system, then every linear combination of them is also a solution. So once you know one solution, two solutions of the homogeneous system, any combination of them will also give me a solution. So you can generate a lot of solutions from only two of them. That's really what means a subspace for us. Okay, so I give a example. I gave you A to be the following matrix. I know that probably you cannot read the entries, but they are actually irrelevant to us. And then I gave you two vectors in the null. What does it mean? It means I gave you two vectors that solve the system Ax equal to 0. So I have to give you two vectors in R4 because the solutions vectors have to be in R4. So I gave you two vectors, U and V. 1, 1, 0, 0, and V. Two vectors in the null. So let's make sure that I am not goofing. Are they in the null? Can we check easily if they are in the null? So looking for my pencil. I don't know what it is. Okay, so are they in the null? So it means if I take this vector here, the matrix, and I multiply it by 1, 1, 0, 0. Do I get the 0 vector? 1, minus 1, 0, 2, minus 2, 0, 3, minus 3, 0. It means this vector is actually in the null. I can do the same with V, multiply it by the matrix A, and I get equal to 0. So both vectors are absolutely in the null. Now my question is, I'm giving you two vectors. It means I'm giving you two solutions of the system, the homogeneous system. Now I'm asking you find 4 other vectors. Is this an easy or a hard question?
Easy.
Easy questions. Because null of A is a subspace. What does it mean to you? If two vectors are in it, any combination, stretching this vector is another solution. Stretch V, another solution. Add them, another solution. Any linear combination of them give you a solution. Because I showed you that the null is a subspace. So you can, once you have two vectors, you have infinitely many of them within it because of the subspace property. And that's exactly what we're doing right now. Okay, so that's one example. For us, that's one of the most interesting example because we're going to need the idea of the null, which represent all the solution of the system. Okay, so that's the example that from linear algebra that we need. The book has another example. I will do it if I will have enough time for that. But that's the important one for us. Okay, now we're going to move to a new idea in a way. Again, another new idea crucial to us, to linear algebra, is the notion of a basis of a subspace. And in 2 words, before I do the definitions, I will ask you the following questions. Suppose I have a plane in R3, for example, okay? And I don't tell you what the plane is. I tell you that I only give you 2 vectors within this plane, only 2. And I tell you H, my plane is the span of those 2 vectors. Before that, let me remind you, I promised myself to do that, no, I forgot. What is, let us recall a basic fact from before I get that. Suppose we have 2 vectors, let us say V1, V2, V3. Okay, before I move on. What do we mean by, let us recall. What is the span of V1, V2, V3? Who can give me a definition?
All linear combinations of those 3 vectors?
Right. All linear combination. So of V1, V2, V3. Crucial, we're gonna need this a lot in this particular section. So now I'm gonna go back to a plane. Here, suppose I have a plane and I'm gonna give you 2 vectors in this plane. So I'm gonna give you the vector 1, 2, 3. And I give you the vector 2, 5, 16 in this plane. So that's one, and that's another. Okay? Am I giving you, if I give you those 2 vectors, and I'm gonna take H to be the span of those. Do we know every other vector in this plane? So if I give you only 2, this one and this one, I tell you let H be the span of them, every possible linear combination. Am I giving you everything you need to know every single vector in the plane? Do I need to give you any other information? No, because if I give you those 2 vectors, it means everything else I can get it as a linear combination of them. Suppose I give you those 3 vectors and then I add a 3rd one, which is their sum. 2 and 5, 6, 7, 3 and 16, 19. Will this new information help you any, or it's a redundant information? So I start with 2 vectors, I take H to be their span. It means if I give you this, I give you everything you need about the plane, because everything else is a linear combination. Suppose now I plop in a 3rd vector, which is the sum of the first 2. I'll tell you H is the span of this vector, and that vector. So it means H is the span of those 3. Will this extra vector important to you?
No.
Does it add anything to the picture?
No.
Anybody else said no? Message?
No.
No, nothing. Because if I know that those 2 is in plane, this is redundant. So what we're gonna say those 2 vectors form a basis for the plane. It means that those 2 vectors give me enough information about everything in the plane. Now, if I take one away, I'm not giving you the plane. I'm giving you just a line. So to give you the plane, I need to give you 2 vectors. If I give you 3, there is a redundancy. It's not important. So this vector, I cannot give it to you. I can give it to you, but it's redundant. It doesn't help in the picture. So we're gonna call those 2 vectors a basis for the plane. It means they are the minimum number of vectors that I will need to be able to span everything in the plane. So we call those the basis of the plane. So let us now go back and define the idea of a basis. So basis of a subspace. Suppose I have a subspace of Rn. So when I say the word subspace, to make it real for you, think of a line in the plane, or in R3 if you want. Think about all of R3. Think about a plane in R3. So have this picture in your mind to be able to interact with the definition. So let H be a subspace. And V1 to Vk are vectors in H, crucial. They are vectors within the subspace. We say that the vector form a basis for H. So imagine a plane. We say that they form a basis if 2 conditions are satisfied. First, the vectors are linearly independent. Second, if I take their span, I get everything in H. It means every vector in H is a linear combination of those vectors. So I have a subspace, I have a bunch of vectors in it. Those vectors form a basis if everything in H is a linear combination of them, and those vectors are linearly independent, which is reflect the picture of the redundancy. I don't want vectors to be redundant. I don't want any of them to be combination of the other. So vectors form a basis if everything in it is a linear combination and those vectors are linearly independent. So let us take example. Today I will take R2 and I will assign, I'm going to take one example, H equal R2. It means my subspace, now I'm going to start with a very basic subspace, is all of R2. It's not the line, it's all of R2. And this is a subspace as we mentioned last time. And now I want to give you example of bases in R2. Means I want to give you example of vectors that everything in R2 is a linear combination and those vectors are linearly independent. Is this an easy or a hard question? I want vectors in R2. So easy or hard? Who can give me one without looking at my notes for a sec? Who can give me vectors in R2 that have the property everything in R2 is a linear combination? That's the idea of the span. And those vectors are linearly independent. Okay, quickly, I want an example. Quick. Anybody?
You could take 1, 1, and 1, 2.
1, 1, and 1, 2. That's absolutely an example. I'm going to take, I will get back to it to this one in a minute. Let's take an easier example. The most easy example we can think of vectors in R2 that has the property everything in R2 is a linear combination and they are linearly independent. What are the most basic vector we should think of?
1, 0, 0, 1.
One's exactly, E1 and E2. E1 and E2. Okay, and then I'll get back to the example that one of you said, which is correct. But first, I want to emphasize E1 and E2. So let me take E1, 1, 0, the unit vector on the x1, and E2 to be 0, 1. Then E1, E2 form a basis. How to justify that? First, they are linearly independent. Am I correct? You guys check it out. Actually, for two vectors, let me again remind you this vector, this fact, two vectors, and 2 is important. Two vectors are linearly 2. The word 2 is important. Linearly independent 2 if they are not scalar multiple of each other. So for two vectors, they are linearly independent if they are not scalar multiple of each other. So E1 and E2 are absolutely linearly independent. And their span is R2, meaning every vector in R2 could be written as a combination of E1 and E2. And in this case, I will tell you why. Because if I give you any vector in R2, suppose I take the vector square root of 2 and E, which is a vector because those are numbers, I can write this as a combination of E1 and, oh, E is bad, pi. As a combination of E1 and E2. Regardless what vector is, I can write it as a combination of that. So it means that every vector in R2 is a combination of E1 and E2. So those vectors satisfies both conditions of a basis. They are linearly independent, and everything in H is their linear combination. So E1 and E2 form a basis. And this basis is given a specific name. That's why I want to really talk about it first. This is called the standard basis of R2. The standard basis of R2. All right, now example number 2. That's not the only basis we have. So we can have different bases for R2. It means we can have other vectors that satisfy both properties. They cover all of R2 and they are linearly independent. And one of your classmates gave me another example. So I forgot the number they gave, but I pick another number. So I'm going to take V1 to be 1, 3, and minus 2, 4. So again, those vectors, I can draw them. So this is my drawing, I think. And let me see here. 1, 3. So this is my vector, 1, 3. That's one of them. And minus 2, 4. That's another one. So that's my V1, and that's my V2. So those are the two vectors. And do those two vectors form a basis? 2. So R2 is huge. R2 is every ordered pair. But those two vectors, two of them, do they form a basis? All right, we have to check. First, check for linear independence. Are they linearly independent? That's the idea. We don't want too many of them. Okay, they are linearly independent because they are not scalar multiple of, or if you try to check for linear independence, it means if you try to check if this x1 v1 plus x2 v2 equal to 0 have a non-zero solution. So if you take this augmented matrix, you realize you have a pivot in every column. It means that they are linearly independent. So linearly independent. 2. Do they cover all of R2? Means is everything in R2 the linear combination. All right, we've seen this probably day 1 or day 2 in class. Geometrically, any vector in R2, I can get to it by moving tiny bit in the direction of V1 and tiny bit in the direction of V2. Any vector could be reached this way. So that's the geometry of it. Now the algebra. So we're going to check that the span is R2. It means we have to check that every vector in R2 is a linear combination. Now we've seen this before. We've seen the idea that any two vectors in R2, if they are linearly independent, then they span R2. That's what we call the invertible matrix theorem. So, but now it's actually reminding you why. This is true because if B is any vector, and we try to solve, I mean, I've asked ourselves, can I write B as a combination of V1 and V2? Okay, I try to solve the system, V1, V2, and B. Ask myself, can I always find those weight? Now, V1, V2, because they are linearly independent, when I find their augmented matrix, that's going to be 1, 0, 0, 1. B will be something. After the row operation will be turned to something else. But now, this is occurring because they are linearly independent. Now, since we have a pivot in every row, it means every row, so there is no issue with inconsistency. It means that I can find x1, x2 such that B is a linear combination. This means that every vector could be written as a linear combination. Hence, V1, V2 is a basis. So R2 can have all kinds of bases, different bases, but all the bases have to have basically two vectors. And that's really where now my idea is. I'm gonna work with R2, and in your homework, you will have R3. So if I take now H equal R2 again, I take V1, V2, V3, 3 vectors. My question, do they form a basis? Those 3 vectors?
No.
No, why not?
You have 3
Basis
vectors in R2, so they're not linearly.
Exactly. Immediately check for linear independence. I'm checking for linear independence. Since we have 3 vectors in R2, we know any 3 vectors in R2 are linearly dependent. Just remember, because when we set up the system, we're going to have a free variable. Therefore, they don't form a basis. So 3 vectors, the reason in R2 they fail to form a basis because they are linearly dependent. Now, let me ask you a question before I move on. How about their span? If I take every combination, all possible combination of V1, V2, and V3, will I actually get R2?
Yeah.
Okay. Will I actually, if I take all the combination of V1, V2, and V3, I will definitely get every possible vector in R2 because the first 2 of them is enough. I don't need the third. So they do span, but for basis, I need the minimum number of vectors required to span. this is redundant. The bases get rid of the redundancy. They don't want redundant vector. They want the minimum vector needed to span your subspace. So in this case, absolutely not a basis because of the issue of dependence. What about if I take V1 to be 1 vectors? Will this form a basis for R2? Which property will fail? Of course, vector by itself is linearly independent. But the question is, will it span R2? It means, can I get every vector in R2 as a linear combination of V1? And the answer, of course, is not, because every linear combination of V1 will be a vector with step on this line. So there is no way I can get a vector, every vector in R2. So V1 does not form a basis for R2. So what's the picture now? So we have now this scenario, and then I stop. I have this scenario. 2 vectors, though they are linearly independent, they're linearly independent, they span R2, form a basis. So 3 vectors, they are linearly dependent, they are not a basis. Even if they span, even if we can get every vector R2 as their linear combination, that's not, the basis requires independence as well as span. 1 vector, linearly independent by itself, but the span is not everything, it's not a basis. So that's what a basis for R2. Now, in my notes, I have also for R3, I did the same study for R3. I want you to read this for next Tuesday, and I will assign problems and we talk more about it. Okay, any questions? All right, before I let you go to take the quiz, exam number 2 is next Thursday. Exam 2 is on Thursday. Next coming Thursday, and your review, which will be one of my old exam, will be up very soon. Probably on Friday, you will have your review. And as usual, on Tuesday, I have one idea I want to talk about, which will be on your exam. It should not take much time at all, and then I will answer every questions you have. Okay? All right, go take your quiz, and good luck. And stay safe, and see you next week. Please, if you have any questions, make sure you email me and I will meet with you. All right? Bye, guys.
And what time is the quiz due?
It's 10 minutes after the hour, I think. 11:10.
Okay, thank you.
Okay, yes.
Mm-hmm.